Hi, this is Sean Murphy of SK Murphy. I'll be the MC for today's PATCA webinar. We're fortunate today to have Carl Angotti. Carl is president of Angotti Product Development. He has developed hardware systems for over 2 decades. Recently, these have been utilized in embedded controllers. His designs also include analog, digital, and mechanical-based circuit interfaces. He often manages larger projects to include other skilled consultants in his designs. He has had considerable experience developing testers for use in medical, industrial, and consumer markets. Carl is a past president of PATCA and a past board member and has been a significant volunteer over the years. He has a BSEE from Carnegie Mellon University, an MSEE from the University of Southern California, and an MBA from San Jose State University. He is a registered professional electrical engineer in the state of California. Carl.
Well, thanks for that great introduction, Sean. Welcome, everybody. So it's funny, we have a variety of attendees today. I see some of you have more experience than others. I am going to interrupt the talk twice in the middle. So I'd appreciate it if we just hold questions until then, or maybe you can put them into the chat, and then we can go over them at the breaks there. But there'd be hopefully it won't be too long between them. Give you a chance to ask specific questions. This talk is going to be, I assume there were going to be people less involved in test when I put this talk together, which means it's going to be at a higher level and not a lot of technical detail, because that makes the presentation very long. So then I have, so anyway, this is the only cartoon I could find about test engineering. And so this is Dilbert now. He says, you schedule the end of the test phase after the start of the production phase. And he says, we're feeling confident. He said, it's too bad that being smart doesn't come with some sort of good feeling like that. Anyway, it's interesting. My agenda, which was a lot more dynamic and larger on the website presentation, it turns out that I got concerned about running out of time, so I had to chop it down. So anyway, I'm going to talk about testing in QA and then various types of testing. This is mostly at a high level, and the economics of testing, tester development, and also question and answer at the end. We'll have, and by the way, I'm willing to stay afterwards if people want to, you know, if it's appropriate. So, boy, this is interesting. Okay, so anyway, tester development is part of quality assurance. So it's almost always formally under QA, although in a startup, sometimes there's not a hard definition there, but it requires design engineers to implement. So I say this skill is often not present in QA anyway, it's often not present in QA, or they have a separate test engineering department in a company. So the ideal person to design a tester is the product design engineering staff, but they often are busy developing the product itself. This is especially true in smaller companies and startups. So, anyway, this presents a special problem then. And so I thought I'd go over a miniature QA product flow diagram, in which I'm just starting here. I'm truncating the process here, where, as you can see, the product to be tested comes in from the manufacturing process. And almost always, I'm assuming, since I'm this electronic engineer, that these are going to be printed circuit boards. There might be other things too, but very often companies assemble the mechanical things are assembled outside the company, except for maybe hard drive companies or other companies like that. So the UUT, or the unit under test manufacturing, has what normally done is that these printed circuit boards are pre-tested, and then they're sent to final functional tests at the end. And this is, of course, before they're going to be packaged and shipped. If they fail this test, then usually they go into failure testing, which may or may not involve the same tester, depending on how it was designed. that was used in failure testing. It was used in functional test. So this is where sometimes some companies do what's called debug in place, which means that they actually debug it when it fails because the card's so expensive or the system is so expensive. In the meantime, when a device UUT fails, then it gets fed back to manufacturing engineering if they have it, or else it just goes straight. Somebody sends it to the process and says, hey, you're building it wrong somehow, so check it out. Or it goes to design engineering, and that means there might have been a design problem in the process itself. Meantime, otherwise, what happens is it gets packaged and shipped, and it goes to either an intermediary, which might be an intermediary salesperson or the customer. Then if it fails initially, if it fails initially, or in warranty, it comes back. And then you have to, when it comes back, it has to be tested to see what was wrong with it. This is valuable information, again, to feed either the manufacturing process or the design engineering, or in this particular case, it might be sent to be refurbished or scrapped, depending upon the value of the product itself. So basically, in types of product testing requirements, there's two fundamental testing regimes. One is engineering design validation testing, and that is, does it meet spec? This is normally done by design engineering. It's extremely rare that it would be done elsewhere. Then there's product verification testing. That is the product built right? Well, this is done by production engineering, and then following that, it's done by quality assurance, or in the QA group, I see in the test engineering portion of QA. So the full product testing requirements of a product itself is normally done by product design engineering, and then it's followed by QA. So basically, software testing is done by design engineering, and ordinarily it's not tested at functional testing. Firmware testing is done by design engineering. And then in modern designs today, there's potentially field programmable gate array or ASIC testing, and that's done by design engineering. That would not ordinarily be tested in functional testing. The device may not function, but that's all that. So then there's hardware functional testing, which essentially is initially done by design engineering, but then ultimately is handed over to quality assurance. The hardware full product testing requirements that a product actually has, especially at the board level, would be the semiconductors and module testing. Now, very frequently today, it's my experience that most people don't test a semiconductor that's coming in unless it's actually has some critical problem with it and they need to be tested for a special reason. The same thing is true with module testing. It's assumed that the semiconductor manufacturing has very high quality assurance, which they do these days, and the module manufacturer has very high quality assurance. And as I said, if there's a problem, then you test, you would test them incoming until they solve the problem. Then, so when you start to build a board, you have bare PC board flying probe electrical testing, which means you test for shorts and opens on a board before you even put the components on it. Because after you put the components on it, the board's worth a lot more money, and if you have to scrap it. So, and then next, in most processes in PCB manufacturing, the assembled board is visually inspected. Now, I'm going to go over all of these in a little bit more detail. And then there's flying probe testing, which is, they can either be simple or complex in-circuit testing, where you test the device semi-operating. So these pre-functional tests, if they're performed, can very often bring final yields, get defects 85 to 95% of the time. So they're able to pre-screen testing, so you don't even have to do functional tests. Then there's final subsystem functional testing, which is what we're talking about here. And if the product goes into a much bigger system, then there's higher level system testing. And that's a bit of an animal of a different color. So anyway, I'm going to stop here to see if there's any questions so far.
So could you clarify a little bit by what you meant by the subsystem testing as the focus of the talk? What's the distinction between subsystem functional test and higher level system test?
Great question, Sean. So basically, oftentimes, unless the product is relatively simple or compact, there's more than one printed circuit board in a system. And so that's why I called it subsystem functional testing. But of course, if the device is going to be, it's essentially the only thing that's going to be done is inserted into a package, or it is already inserted into a package, then that becomes the final system test.
Carl Becker, you made a comment that you used your Mark I eyeball to do visual test. Can you talk about what that was like?
Yeah, that was circuit boards. I guess at the time there was a room where they had a machine that put the components in and soldered them, and they would come out of that room and be passed on to the group that I worked in, and we would sit at a bench and inspect all the soldering joints, as well as confirm that the parts were in the right place, or they were the correct parts that were there.
Yeah,
so there were about 9 basic boards, and they were pretty complex, big at that point in time, 1978. And I think I had all the part numbers memorized for all 9 boards.
Yeah, I'm going to go into that in the next set of slides. So I will show you how it's done more in a more modern setting.
Any questions?
I imagine it's changed.
I had one question. The idea of pre-functional testing, being able to catch problems early on, right? Is that the general idea there?
You're trying to locate manufacturing defects, right? And you may as well catch them. The important thing is that the further it goes on in testing, the more expensive it is. And I can tell you, some of these testers are quite expensive too, these pre-functional testers. And
Yeah.
I'll go a little bit further into that in the next set of slides.
Okay. No, because the kind of the follow-up to that was a lot of times in any kind of technology, software, hardware, the problems also don't start manifesting until you've integrated a lot of different components together, right? So the initial functional testing, yes, I agree that it could catch things in early stages, but a lot of problems always show up at the end, right? when you integrate everything in, that's when you find out that, yeah, the right hand isn't talking to the left for some reason. We didn't source our vendors properly or something, right?
Yes, and it depends upon the complexity of the system.
Yeah.
For example, I built a tester where they were building devices at the rate of 10,000 to 20,000 a month in batches. That's a completely different process than, it's done differently. And of course, they have more cash flow to deal with. These things are sold worldwide in the millions. So it's a completely different process from what we're going to be talking much here. And of course, you use statistical things where you do sample testing, where you don't test all the units, you just test a fraction of them, and you use statistical methods to determine how high the quality is. I think maybe we should move on, Sean.
Okay.
So let me go here. So I just wanted to show an example of a flying probe tester for bare PC board. And so here you can see these tests are normally what used to be referred to as shorts and open tests. And so they're usually what you test is the places that are supposed to be open, and other places where it's supposed to be shorted. And most of this information is derived directly from the PC board layout. there's a tools that actually do this now, where they extract that information and actually create where you probe. And this is normally done at the board manufacturing level, not at the company. So, but this is the first level of filtering out, because no sense in stuffing a board that has $500 worth of components on it to find out that there's a problem with the PC board itself. And of course, other tests are made with PC boards too, if they have troubles. And I don't want to go into details about that now, but they're more mechanical. So this is a modern automatic optical printed circuit board inspection system, and there are many of these now. Actually, this is not the finest one. I just couldn't locate the ones that I've seen in practice. But in this particular case, what they do is they take a good board, well-made board, shoot a picture of it, and then they use video processing to determine anything that's different from the original, and they focus directly on it. So the person is actually there, but unlike, I forget who it was describing it, but in the old days, you had to use a microscope and it slew the board back and forth and try to find bad things. This one here immediately locates them because it shows you just the difference. This place is wrong, this is wrong, this is wrong, magnifies it, and you can immediately determine what's wrong and then reject the board. So, so it says here is locates missing parts, which is real common because they're being fabricated now by automated machinery. You can have a misalignment, which ordinarily can cause field problems. And then you have, I've never seen tombstoning myself, but apparently they claim it happens. And you can also locate upside down parts, which sounds kind of like, this is for surface mount parts, but very often the value is stamped on one side of the part, so you can't tell what kind of part it is. And so upside down parts are a problem for sure. And then this is another tester, which is, this is also, by the way, each of these tests you have to pay for in order to have them done. If you are manufacturing a product, you may or may not use them, but almost everyone uses visual inspection. And then, and almost everyone will at least sample test shorts and opens on a bare board. I mean, it would be foolish not to do that. When you have an expensive board, you almost always pre-test it at the PCB manufacturer for shorts and opens. Now, this particular test, in-circuit test, is much more complex because someone has to guide the testing, and they have to have some knowledge of the circuitry, and it's quite expensive. But so you need a skilled operator for the machine, and what they do is they power up the component, and then they measure different points in the circuit. And of course, they're not good for anything that goes very fast. Anything over 10 kilohertz or so, it'd be ridiculous to measure this way. But they do have some useful tests that can be performed on boards. That's a judgment call by the person that's doing it. So now I'm going to get into what I call economic considerations, which are very often people that work in test engineering don't consider these things very much. At least I've noticed. It's what the management does, and sometimes a well-informed test engineer understands. So the question is, what are the economic considerations of building testers? So the product costs to consider are non-recurring engineering costs, NRE, and they are product development costs and tester development costs. As testers get complicated, they can be quite expensive for complex systems. Then there's recurring device manufacturing costs, which are product manufacturing costs themselves, which the engineers very often focus too much on. And then there's the added testing costs as a percent of manufacturing cost that adds directly to the selling cost, just like it was a part. And so one has to determine. Well, I'll get into this a little bit more, and so for future slides, so you can understand. So each test done on a device under test, the DUT, adds to the device cost to produce the product. Functional testing is often the most expensive testing performed on a device. Almost always is the case. Usually only a small number of such testers are produced. So as a result, when you make a tester, you usually try to use as much outside resources as you can, as you buy as much stuff as you can, then you lash up the tester together. But very often it requires you to have an embedded control system controlling all this testing that's going on. And then, of course, you have to write test procedures to have that happen. So then this comment here is that there are numerous factors that go into the decision to create a functional tester. And I'm going to go into some of these factors now so that you can understand a little bit more about the decision to what kind of tester to build. So when you look at the final production tester economic considerations, you say, what's the cost of tester development, the NRE? What's the cost of the test operator? That's a variable cost that adds directly to the product cost. And that means, do you need to have an engineer do the testing? Can it be a highly skilled technical person, maybe we used to call them super techs in the old days? Or can you downgrade it more and more and more till you have less and less expensive variable costs by the person? And also, if a person has high skills, it almost always requires a lot more work on their part, so the cost goes way up. Then what a lot of people don't consider is the cost of field applications person and the field debug and test. So oftentimes larger systems are sent into the field and they don't work when they get there, or they fail. And so then they have to go out and do field debug, and that's very expensive. That's another variable cost. Hopefully only a fraction of the units have that problem. The cost of determining field failures by QA and engineering. So that means if the parts come back, who's going to do the determining what's wrong so you can get it fed back into either manufacturing or design. So basically another problem area in developing systems is circuit complexity in the device under test. The more complex it is, the more it costs to build and also to do the testing. It takes longer, no matter who's doing it. If you have radio frequency testing, which means that usually today it can be up in the gigahertz region, you have to have specialized testers and or specialized signal routing and other things in order to do the testing. And that adds to the cost tremendously. Plus it can add to the cost of testing if it's done manually, which sometimes it is, where they use hand probing. Now, I didn't discuss that earlier. Hand probing is very time consuming, where the test operator takes a probe and puts it in different places in the circuit in order to validate testing. Sometimes it might be an oscilloscope. And modern oscilloscopes now assist in that. High clocking speeds. As I say, anything beyond 100 kilohertz to a megahertz is definitely going to have to be handled specially. It can't just be done with a simple output connector or whatever. Then, of course, there's high precision in the analog circuits, if they have analog circuits in the system. These circuits have to be at least as precise and likely more than 5 times, often 10 times, as precise as the device itself. So the tester has to be very well designed. And of course, depending upon the situation, measurement in the noise level can be a very strong concern, where you're looking at signals very low in level and the clock noise on the board is quite challenging indeed. Anyway, I'm going to stop here and see if there's any other questions.
Questions for Carl? We used to have a rule of thumb that the cost of a defect went up by a factor of 10 after each major step. So is that part of your calculation here, that you're trying to catch defects as early as possible to when they've been inserted into the process?
Absolutely. That's the whole name of the game, right? Earlier you can detect them, the better. And yeah, and I don't know that the factor of 10 holds, but certainly in field work, it certainly is often 10 times. And so, especially if you ship stuff that's bad into the field and it's complex, and you have to send highly skilled people to go out to determine what's wrong, it can be very expensive.
Charles Nolan made an observation that temperature control of the device under test is also critical.
It can be, yes, indeed, it can be. And again, that would be circuit precision perhaps, and or in the military, for example, when we used to do testing for military products, they have to operate over a very wide range, like minus 55 degrees C to plus 125, which creates a lot of other problems. And very often in that particular regime, which is well beyond the scope what I'm talking about here, they actually run temperature runs, pressure runs, humidity runs simultaneously while shaking the hell out of the product. I can tell you that's a really difficult test regime. And of course, they spend a lot of money on tests to do that. Okay, so shall we move on then?
Sure.
Well, this is going faster than I thought it would. So, the important thing to me is when one's going to start a tester development project, what you want to know is, are you going to be doing, what type of tester are you going to be building? As I think I mentioned this a little bit earlier, so you can build what's often referred to as a manual tester, where the individual twists all the knobs, sets everything, puts the signal in, makes measurements, and then decides if the circuit is working properly. And in its minimal form, that would be what the design engineer is often doing. That's what they're doing. And so it requires the highest operator skill, and of course, therefore, has the highest wage rates. It's very costly, slow and costly. Well, it's the slowest test time, and almost all the testing that's done is manually recorded. So there's no automation there. I've seen, other than you can actually have a program in which the tester could actually enter data manually so it can be analyzed later, but ordinarily not so. But sometimes a device is so simple, maybe that's the best tester to build, or you're building a very low volume of a cheap product or whatever. So, and then the next kind of tester I refer to as semi-automatic testing. And that is where there's much less intervention of the testing now. There's less manual probing and less interpretation by the operator. And so what happens ordinarily in these kind of testers is that the test engineer sets up the tests so that the system is set up automatically, and then the analysis of the data coming out is done a little more manually, so that maybe they might even do something like look at a voltmeter and answer a yes or no question, and then automatically record that. And so there's just less probing and certainly a lot less interpretation by the operator, which means you need a moderate operator skill. So they have an intermediate rate of pay. And then you have a much shorter test time. And also it depends, human beings being in the loop, no matter how much you try to avoid it, they make mistakes. It's a rote process, because if they're testing a number of units, let's say a batch of 100, I mean, anyone thinks that this is trivial, but if you go through 100 things, and if any design engineer that's ever done that never wants to do that again, that's really a bear. So anyhow, so there's semi-automatic testers, and then finally, there are fully automatic testers, or almost, I say 90 to 100% because almost always there might be some manual probing involved. So you have very little, if any, manual intervention of the testing. And you have none or almost no manual probing and virtually no interpretation by the operator if you can avoid it. So this has the very lowest operator skill. And you have almost always have fully automated test recording. In addition, when they get this sophisticated, almost always this recording the data is gathered in a special way and moved up level so that you can do tracing of failures and other things automatically with other programs that view what's going on automatically and alert the manufacturing process that there's a problem trend. This is especially true in these, Six Sigma type environments where you really don't want any product coming back. Let's see here. So in this case, then there's a decision to be made. Should you use manual, semi-automatic, or fully automatic testing approach, because that impacts a lot of things further on down the line. So the factors in making this decision, by the way, I'm going to be talking about a methodology now that assists managers in making decisions about what type of tester to build. Ordinarily, a test engineer wouldn't necessarily make this distinction, but I'm making it now, and it would be good if test engineers knew more about these sorts of things. So like factors are, how much experience have you had with building similar testers? Like if this is the 6th modification of a product, probably you're going to use almost the same tester to test the next level up one, especially if it's the same platform. And then there's the final estimated cost of the UUT. If it's very small, you can't spend much testing each unit, or you're going to have to go to statistical techniques. And there's a volume level of the nominal build. That's how many you're building at a time in batches. And of course, there's the skill level of the operator. There's funds available for the tester project. And then there's a volume level of the estimated life cycle build, funds, which means that you want to try and estimate at the beginning how many of these things you're going to make over its entire life. Because remember, life cycle is really critical now in product manufacturing. And so basically, this provides the funds to feed back to R&D for the tester, so that if a manager is going to make a decision, the question is, if there's a large number of these going to be made over a long lifetime, then of course it's worth more investing in higher level testing. Then there's the cost to build the tester and write the software or the test procedures. That's another factor, which very often in testing, that cost exceeds virtually almost all the other costs today. Just programming the thing to work properly. Then there's the likelihood of field failure, of course, and the cost of supporting field failure. And so what I'm going to do now, I'm going to give an example. I'm going to go out of my talk here. So what I've developed here is a methodology which you learn in places like business school to help make decisions. Now they don't make decisions. This is a messy thing for engineers. They do not understand the concept. But if you're going to decide to do something a particular way, some managers, just from their experience, say, we'll do it this way or that way. But a method that could enhance that, it doesn't make the decision for you, but it enhances the possibility of making a decision, is to take these factors, like I mentioned, and put them into some sort of a sheet, an Excel spreadsheet, which I've developed for this particular one, and which you say, well, how valuable, how important, I should probably say value, but how important is this factor on a scale of 1 to 5? And what this allows you to do is it allows you to rank the factors. See? And then you say, well, if I make a mistake, what's the impact of that error over here? And then what you do is you multiply this number times this number to get a number over here. And in the end, you end up with a bunch of estimates, if you will, of how important that particular factor is. But what you're interested in is the accumulation of all of these. And so what I do here is I do this all this a bunch of fancy math on an Excel spreadsheet, but I say that the calculated value, the computed value is 0.44, which is a normalized value, where 1 is definitely you should be using an auto tester. Mid value is 0.36. It says semi-automatic likely, but maybe trending towards some more automation. And then if it's 004, it means they all have 1s. Well, that doesn't make any sense if they're all 1s, but nonetheless, that would be the bottom of the circumstance. So let me stop sharing again. And then I will go back to share screen and go back to my talk. All right, so let me oops, I hit the wrong one. Well, anyway, I'll just scroll down quickly. And then the next thing I wanted to talk about beyond this is the way a development of a tester works in terms of planning purposes. So, and I'm a big believer in waterfall. I'm not too much into agile and hybrid methodologies, but they do work. Just I haven't seen outfits use them. So in the meantime, you can see that the phases of a tester development look an awful lot like they do for a regular development. The only difference is right here, hardware off the shelf. You're going to buy a lot of off the shelf stuff, which sometimes has long lead times. But then you're also going to build a printed circuit board that essentially allows the test to proceed in an automated or semi-automated manner. And so basically what you have is you have a hardware design phase, hardware block diagram, hardware selection, etc., spec phase. And then by the time you're done with the spec phase, you start doing design. And so you have a custom printed circuit board design fab. It's just like a regular development. Only difference is the integration of externally purchased hardware. And then this also says if the tester has mechanical, then in parallel, you're going to have a mechanical development project. I've worked on 1 or 2 of these in my career that were fairly complex. And so now you've got to generate a mechanical spec. You've got to purchase these mostly off-the-shelf parts. If a company is not in that business, probably not a wise idea to be building that. And then you have to integrate that. Then you have to do the software design phase. That's another phase. Then you have to do the hardware, firmware, software integration. This is where things get really bad. And then you have introduction to production and then release to production. So anyway, that pretty much wraps up my talk. It went much faster than I thought, but I'm open to any questions you have. By the way, I have I'm going to put into the chat window some of these things, but I publish a lot of papers in this particular area, not a lot, but enough. And you can go to my website, angotti.com, https angotti.com, tech resources news, which means newsletters, HTML. And you can see a lot more about this stuff that I've written about. It's not covered here. Okay, more questions or whatever.
So I was trying to find, you've got that chart on your site, or do they have to write you to get the ROI calculation?
Yes, I'm sorry. Yes, if you want to get the actual thing, just send me an email. And let me go back out of here again. I'll stop sharing. And I have I have this saved somewhere. So let me there's two things I'll put in the chat. If people are interested at all. So this is direct links to the tester portion of my website, and also my actual, oh, I didn't put that on there. I forgot. My actual, if you want to get that spreadsheet, here's my email address. So any further questions anybody has, or ideas, or we didn't get any input, like, I don't know, Peak, did you learn anything about anything you wanted to know here?
Actually, I'm a web tester, so I'm not familiar with the hardware
Ah.
testing at all.
Okay, gotcha. And I think, is there anybody here, once you raise your hand, that actually does hardware testing? I think Joe Zot, I don't think we met you. Neil? Oh, you're muted.
Muted. Okay, there we go. No, this is a really good perspective. A lot of the testing that I've been involved with has been kind of the high mix, low volume aerospace type of testers, RF measurement systems, things like that, which again, a lot of those things also apply, like temperature control for accuracy at higher frequencies and those types of things. But this is a really good perspective, because this presentation, I think it covered a lot of things there that, you know, I kind of already had some awareness of it, but the way you presented it, I think was really good in terms of all those variables that go into, putting a production tester together. And I think there's one other variable there that I see in the industry is the build versus buy
Yes.
decision that a lot of companies go through. And I think there's a matrix there to be had there as well, which is what makes it cost efficient to build in-house. Do I have the skill sets to build a system in-house versus source it to a system integrator and that type of thing. So thanks for that. I think it was a really good presentation.
Oh, thank you for
So-
that. You
So we
bet.
had a question from Chris Capadia and then Chuck, but I'll go to Chris first. Chris asked, in what phase of,
I was just gonna make a comment. I just want to let you know that in the military, these expenses are gigantic, a huge part of the project. Okay, so Chris's question?
at what phase of product development should you start thinking about the testing?
Well, if you're a test engineer, you think it's the day you conceive of the product. But you know, at least once you get along where you've at least got a system description and a system block diagram, from then on, it's likely that one should start considering it. But it's very difficult to get too much done until at least you've got the system spec put together, if that's any help. So we're gonna go to Chuck's question, I guess.
You need to go ahead.
Go ahead.
Okay, thank you. We found in semiconductor across quite a few companies that I either worked for or consulted, that the problem was in the actual contact interface and interface board. When they first grabbed them from the side, the early dual inline, dead bug type of package, finger breakage was a significant problem. I got hired for that.
Mhm.
It was a nice ride, by the way, while it lasted. Then in those military, you mentioned that minus 55, trying to maintain the short distances required by the tester manufacturer. Teradyne 8.5 inches from the pin in the tester test head to the device under test pin, and not have the cold conduct out nor have heat leak in and disturb the device under test temperature. So those were some very fun areas to work on. Did end up getting one patent there.
Yes. And
Carl, have you done that kind of work? This is something I haven't asked you clearly enough in past patents.
no, I have never done that kind of work myself. Although I do know, a lot of the product manufacturing companies, they do what's called burn-in test, a hell of a lot of that. And that's done very often on expensive components. And then what they do is they test them before, burn them in for a while, and then test them after. And they use all these automated testers. I mean, that field is well developed engineering wise.
And you,
Someone does still have to write the procedures.
oh yes, you get some real fun things.
Yeah.
We were working with high-speed logic SRAMs for the military. And simply because of inductance, we started getting 12-volt spikes because of oscillation. And we were doing the simple, just wiggle all the inputs with oscillators. It wasn't a program pattern.
Mhm.
We literally had cracked devices and melted sockets just from resonance.
Okay, wow. So again, one of the things about test engineering is that it covers such a wide range of stuff. And especially, we get a product that has a lot of mechanical. One system I worked on one time, a while back now, was for applied materials. And they build giant semiconductor test robotic systems. I mean, testing those things is really something else. I mean, they got all kinds of mechanical robots running around, and anyway, very complicated systems. And of course, they sell them for a large amount of money. They spend a lot of time testing them, and then eventually they go in the field and they don't work. They're the ones that don't work because they're so complicated. Getting all that mechanical and electrical stuff working together fast. Everybody wants faster, right? Faster.
Other questions for Carl based on today's presentation?
Wow. My goodness, class is going to get out early today. Well, I'm willing to stick around if anybody wants to ask any questions. There was someone wanted to know about the process itself of putting a team together.
Right. There was a question from Sammy about how do you actually pull together these product teams and organize and manage them? Any tips on that?
Yeah. Huh. Boy, that's a really big challenge, because anybody that, I'm a consultant, so I only work with people that have fairly high levels of skill that can ramp up rapidly. If you really are doing something complex, you have to count on 6 months of learning from someone just coming into the process to learn how to do it. And so building a team is very challenging indeed. And of course, the worst problem, well, anyway, so to build a team up, you have to live with the resources you have available in a company. And maybe you can at least get some of this more skilled person whom you said, gee, what I want is all the best people on my project. And it turns out that you may get them, but they only last a half an hour, and someone pulls them off to another project and disturbs everything you've been trying to do. So anyway, maybe I could talk to Sammy a little bit more offline or something about the more Type Talk at Work by Otto Kroger. Oh, okay. Maybe we could spend a little time offline talking about experiences with that.
So, Carl, do you have any kind of final summary remarks, and then we can have an informal networking afterwards? You can talk to Sammy.
Yeah, I think that if you're interested in this subject at all, it'd be wise to go look at some of the other papers I've written. which go into different other areas of details, and a lot of them are more technical. And I wanted to try to be less technical today, even though I was still a bit technical. Just imagine what the technical stuff looks like. But anyway, of course, if you have any reason that you want to ask any questions of me, I'm always open to answering questions from anyone. That's all I can say.
And then I put Carl's email address in the chat too, if you wanted to follow up with him privately.
Yeah, I'm very open to it. So if I don't answer the phone, it's because I'm a bit distracted elsewhere, but just leave a message. I will return the call, and reasonably soon. You know, I'm not one of those people who says we'll get back to you as soon as we can, and it's 2 weeks later, you know. That doesn't sound like a valid thing to do. All right, should we let class out early?
Yeah, I think we'll break here then. Thanks everybody for coming. Carl, great talk. Thank you very much.
Well, thank you.
All right.